Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 3.2 from your textbook, continuing our investigation of our new property of matrices, the determinant. So, to start off with this video, what we're going to do is we're going to look at sort of an important computational theorem that tells us that calculating the determinant of an upper triangular, lower triangular, or diagonal matrix is actually quite easy. We actually sort of saw this in the very last sort of horrendous example that we did from section 3.1, which is where we took that 4x4 matrix and we went through all 24 different permutations, and we saw that only one of them contributed a non-zero value, and that was because the matrix was actually upper triangular. And the only one that contributed a non-zero value was the diagonal product, the permutation, the sort of natural permutation where P1 is 1, P2 is 2, so on and so forth. So we were choosing A11, A22, all the way down to ANN. It turns out that that was not a coincidence. That is true in general whenever you are working with an upper triangular, lower triangular, or diagonal matrix. So, this theorem says if A is an upper triangular, lower triangular, or diagonal matrix, then the determinant is simply the product of the diagonal elements. This theorem tells us nothing about the determinant of non-upper triangular, non-lower triangular, or non-diagonal matrix, so you can't use this theorem on just a everyday sort of random square matrix. But once we sort of taken a look at how determinant is impacted by elementary row operations, one computational technique for calculating the determinant of a sort of random or arbitrary matrix is to use elementary row operations to put it into one of these formats and then use this theorem. So this is an important sort of computational theorem here. So we're going to do a proof for this. For one particular case, we're going to prove it for the lower triangular case. In your textbook, they prove it for the upper triangular case. And of course, a diagonal matrix, well, you could prove that separately, or you could just remember that a diagonal matrix is simultaneously both upper or lower and lower triangular. So if we complete our proof here, technically we've proven it for this one and this one. You can read your book for the proof of this, and of course if you read the proof of this, then this also applies to diagonal. So either way, we've covered all three cases. So let's go ahead and look at a proof for the lower triangular case. So we're going to assume that A is lower triangular. Remember, lower triangular means that if you have a square matrix and here is your diagonal, these things over here can be whatever you sort of like. I don't know why I made that so messy looking, but this stuff over here, the stuff above that diagonal, all has to be 0. So we're going to assume that A is lower triangular. Remember that that means that the elements Aij are going to be equal to 0 when I is less than j. Whenever that column position is larger than the row position, if you think about what that means, right? Column position being larger than the row position means that you're going to be over in this sort of upper triangular section, which has to be 0 if you're going to be lower triangular. So if we assume A is lower triangular, then we know this is 0 whenever I is less than j. What happens when I is equal to or greater than j? Well, we don't know. Those could be non-zero. They could be 0. It doesn't matter, right? The only thing that sort of matters is that if it's lower triangular, then everything where the row element or the row position is less than the column position is guaranteed to be 0. So what we need to show is we need to show that the determinant of A is equal to A11, A22, down to ANN multiplied together. So how are we going to do this? Well, we have that strict definition of what the determinant is. So we'll start our proof here. So proof. So determinant of A. What do we know about that? Well, we know that that is the sum over the n, that's a little messy looking, over the n factorial different permutations with the sign of each permutation, P1, P2 down to Pn, times A1, P1, A2, P2, down to ANPN. So there we go. Okay, so let's go ahead and analyze this. Remember, this is a giant product. This right here is just either -1 or +1. So this is what determines whether or not something is 0 or non-zero. Keep in mind, since this is a giant product, if one of these, if just one of them is 0, then the entire product is 0. So what we're going to do is we're going to consider when A1, P1, A2, P2, down to ANPN is potentially non-zero. Now, we're saying potentially non-zero because, again, there could be instances where maybe it is 0, but we're not going to be interested in that. What we're going to be interested in is just where it's potentially non-zero. So in other words, we're going to rule out everything that we know must be 0. All right, so let's consider when this is potentially non-zero. To be potentially non-zero, each of these needs to be potentially non-zero. So A1, P1 is potentially non-zero. Well, let's use our definition of the lower triangular form. For this to be potentially non-zero, we know that whenever the column position is larger than the row position, then it's automatically going to be 0. So in other words, to be potentially non-zero, the row position needs to be greater than or equal to the column position. Well, the column position is unknown. It's the P1. It's whatever the first element of our permutation is. But the row position is known. It's 1. So the only way that this is going to be potentially non-zero is if P1 is equal to 1. If P1 is anything else, 2, 3, 7, whatever, then this is going to be larger than that, which means it's guaranteed to be 0. So the only way that A1, P1 is potentially non-zero is if P1 is equal to 1. Now let's consider A2, P2. So this is potentially non-zero. Well, again, this one would have to be smaller than or equal to this. As soon as this is greater than 2, well, then we automatically know by the definition of lower triangular that that is going to be 0. So that means P2 needs to be 1 or 2. But if we think about it, we know P1 must be 1 to be potentially non-zero. And remember, a permutation, every element is distinct because you're permuting the first n numbers. You can't have any repeats. So if we know P1 is equal to 1, then we know P2 can't be equal to 1. So that means P2 must be equal to 2. Well, for A3, P3 is potentially non-zero when P3 is 1, 2, or 3. But notice that P1 must be 1, so it can't be that, because again, permutations are distinct. And P2, now we know it has to be 2, so P3 can't be 2. That means P3 has to be 3. As you can imagine, this logic continues down to AN, PN is potentially non-zero. Well, Pn could be anything. It could be 1, 2, 3, down to n. But every one of the previous ones will have ruled out everything except for n. So in other words, P sub n has to be all this stuff. So that means if we're sort of circling the one that it has to be, P1 has to be 1, P2 has to be 2, P3 has to be 3, and Pn has to be n. In other words, P sub k has to be k. So what we've just figured out is the only potentially non-zero A1, P1, A2, P2 through AN, PN. The only potentially non-zero product of those elements is when you have permutation 1, 2, 3, down to n. Every other term is guaranteed to be 0. So in other words, in this giant sum, which is the definition of the determinant over those n factorial different permutations, only the permutation with P1 equals 1, P2 equals 2, P3 equals 3, Pn equals n is going to have a potentially non-zero term. Everything else is 0. So this tells us that the determinant of A is just the sign of that permutation, 1, 2, 3, down to n, times A1, P1, which is A11, A2, P2, which is A22, because again, we're following this permutation, down to AN, n. Final thing to sort of do is, what is the sign of this permutation? Well, this is the natural order, meaning there are no inversions. So this means that the determinant of A is -1 to the 0, A11, A22, down to ANN. So -1 to the 0, you can just think 0 is an even number. You could say anything to the 0th power is 1. So we get the determinant of A is A11, A22, down to ANN. Check. And that's exactly what we wanted to prove. So if you read through your textbook proves this for the case where it is upper triangular. Their logic is reversed. They actually start by analyzing when a and pn is potentially non-zero, and they show that that has to be n. Then they move to an minus 1, pn minus 1, and show that that has to be pn minus 1. And their last one is showing that a1, p1 has to have p1 equals 1. So it just reverses this because for upper triangular, this condition is reversed. But the logic is very, very similar. So now that we've proven this, we basically know that in these cases, in one of these three cases, either upper triangular, lower triangular, or diagonal, we have a very easy way to calculate the determinant. Unfortunately, most matrices are not in one of these three forms. But the next thing we're going to discuss is how those elementary row operations impact the determinant. If we can understand that, then we can use those elementary row operations to put a matrix into one of these three forms, and then use this theorem to very easily calculate its determinant. So we're going to begin talking about some properties of the determinant. And we're going to do a few in this video, and then we'll do some more in later 3.2 videos. So let's start off with three basic properties of the determinant that all relate to the different elementary row operations. So elementary row operations and the determinant. So we're going to have three properties here, one corresponding to each elementary row operation. So property 1, if B is constructed from A by interchanging two rows, so if you interchange two rows of A, then the determinant of B is equal to the negative determinant of A. So in other words, interchanging two rows, performing that first elementary row operation, negates the determinant. Property 2 says if B is constructed from A by multiplying a single row by the non-zero scalar k, remember that's our second type of elementary row operation, then the determinant of B is k times the determinant of A. So multiplying a single row by a non-zero scalar impacts the determinant by that same non-zero scalar. As a quick follow-up to property 2, this would be considered a corollary to property 2. If matrix B is k times matrix A, so in other words, matrix B is a scalar times matrix A. Well, keep in mind that if we consider A to be n by n, then this scalar multiplies onto each of the n rows. So by this property, you multiply n different rows by the non-zero scalar k. So in other words, this factor of k happens n times. So the corollary to property 2 says that if matrix B is k times matrix A, then the determinant of B is k to the n determinant of A. And all that is applying property 2 for each individual row. And since we assume that A is n by n, that's n rows, n factors of k. All right. Finally, for property 3, if B is constructed from A by adding a multiple of one row to another row, so remember that's the third elementary row operation, well, then the determinant of B is equal to the determinant of A. So in other words, performing that third elementary row operation does not change the determinant. All right, the big corollary to properties 1 through 3 is that if B is row equivalent to A, then there exists some non-zero scalar C, such that the determinant of B is equal to C times the determinant of A. All this is basically saying is that these three properties, property 1, property 2, property 3, if you perform a series of elementary row operations, well, each elementary row operation is either going to negate the determinant, multiply the determinant by a non-zero scalar, or not change it at all. If you do a series of those, maybe you negate, you multiply, you do this, you multiply again, you negate again, you do this again, you negate again, whatever. Once you put all those different factors together, well, every one of these is either multiplying by a negative one, multiplying by a scalar, or not doing anything. That means that by the end, if you do a whole series of them, the determinant of B is some scalar times the determinant of A. The whole point of this, though, is that you can basically track those manipulations, and if you sort of reverse them, then you can determine the original determinant of A, right? This would also imply that the determinant of A is 1 over C times the determinant of B. So you can sort of go back to your original one and figure it out in terms of your new one. So this is just saying that if you combine them in some series, well, you just put all those constants together, and it's going to be some constant times the original determinant. Okay, so these are very, very important properties because they tell us how the elementary row operations that we studied back in Chapter 2 impact the determinant. For right now, we're going to go ahead and prove property 1 and property 2. Hopefully it's clear where the corollaries come from, so we're not going to give any formal proof of those. We will return in a later sort of video on section 3.2 to proving property 3. And the only problem is right now proving property 3 is a little bit messy because we just need a few more things to sort of talk about. But for now, we'll talk about properties 1 and 2. We'll prove those formally, and then we'll take a look at an example of using this to actually calculate a determinant more efficiently than using that sort of brute force definition. So let's talk about proofs of property 1 and 2. So for P1, we need to say B is constructed from A by interchanging two rows. And we need to show that the determinant of B is equal to negative the determinant of A. Okay, so let's do this. Let's say without loss of generality. So we can, without loss of generality just means that even though we're going to make an extra assumption, it doesn't really change anything. Without loss of generality, let's assume B is constructed from A by interchanging row R and row T. So we're just going to give names, row R and row T, and we're going to assume R is less than T. So in other words, R is the first row and T is the second row in terms of like reading down, so in terms of the order of the rows, and we're interchanging those two. Okay. All right, notice that that allows us to say that Bij, the ijth element of the B matrix, well, it's Aij if you don't happen to be in one of these rows. So if I is not equal to R or T. It's Tj if I is equal to R. So if you're in that rth row of B, that's the tth row of A. And it's Arj if I is equal to T. So the rth, or the tth row of B is the rth row of A. That's what it means to interchange here. So this would just be saying what the elements of Bij look like. All right, let's go ahead and talk about the determinant of B. The determinant of B, of course, by definition, is that sum over the n factorial different permutations, the sign of each of those permutations, times the product of those elements, A1, P1 down to Bn. Excuse me, because this is our matrix B here. So this is B1, P1 down to Bn, Pn. Okay, that's the formal definition of the determinant. Okay, let's write this out a little bit more thoroughly, and let's mention the sort of important moment when we hit the rth row and the tth row of B. So we can say that the determinant of B is actually the sum over those n factorial permutations, the sign of each permutation, and let's also include that in here. So we'll say that this goes down to P sub R, and then P sub T, and then P sub N, and then B1, P1, and then all the way down, first one we'll hit is BR, PR, then we'll continue down to BT, PT, and then we'll finish at BN, PN. And again, this is why it was important to say R less than T, because we can sort of say that the R ones happen first. Okay, let's replace these in terms of A. So we can say that the determinant of B is the sum over those n factorial permutations, P1, PR, PT, Pn. Now, of course, right, these ones, things like this and things like this, they correspond to this definition here, which says that those elements are exactly the same as the ones from matrix A. So when we do that, we would just have A1, P1, and down here we'll have AN, PN. These, of course, these two specific ones here, they actually match these definitions here. Okay? So this would mean we would go down then to, this would be ATPR, right? Because this is the rth row of B. So this would rth row there. That means we use this one here, so ATPR, and then ARPT. Okay. So now we have the determinant of B in terms of this. Now you'll notice, right, that this is just a multiplication. So let's put this back in sort of the normal order, right? R is supposed to be first. Commuting this as just a multiplication, we can just interchange these two. Nothing changes there because normal scalar multiplication, which this is of course commutative. So let's go ahead and just use a different color to sort of indicate what we're doing. We're going to take these two, interchange, and just remember multiplication is commutative. Normal multiplication, right? Matrix multiplication we know is non-commutative, but these are just scalars, so we can put them in any order we like. So we have the determinant of B then is this sum over the n factorial different permutations, PR, PT, PN, A1, P1, down to ARPT, ATPR, ANPN. Okay. Now, for this to actually fit the definition of the determinant, each of these is supposed to match up with each of these. So you'll notice, well, something is sort of off. We hit P sub R here in our permutation, but we use P sub T as the column position for this. And that happened, of course, because we went from B to A. So what we need to do is we need to get this to match the sort of order that we use the permutation in. We need P1, P2, all the way down to PT first, then PR, then PN. So we need to interchange these two. This is why we spent some time proving those things about the inversions and the sign. We know what happens if you interchange these two, right? If we now interchange these two positions, right? So in other words, we use the permutation in a different order so that this actually matches how we're using it in this definition. Well, we said that if you swap any two elements in a permutation, you negate the sign. So this is now the determinant of B, the sum over those n factorial permutations, negative the sign of P1 to PT to PR to PN, A1P1, ARPT, ATPR, down to ANPN. Now you will notice that these are used exactly in the order that they're over here. So this is how we set up the definition of the determinant. So what we can do is we can factor that negative sign out. Determinant of B is negative the sum over those n factorial permutations. If you wanted to be really thorough here and, sort of write it out with even smaller steps, the next thing you could do is instead of having it be in this sort of weird order where it goes PT then PR, we could define a new permutation like Q1 down to QR down to QT down to QN, where now those would match with these. That's unnecessary though, because as long as this is in the same order that the column positions are, then we know that that's the definition. Now we can say that this whole expression here, right, this whole thing, that is the definition of the determinant of A. So we get the determinant of B is negative the determinant of A. And that's what we wanted to prove. So that proves property 1 there. The whole key thing here is basically understanding what interchanging the two rows meant in terms of the elements of B, making use of that here, recognizing that this multiplication we can put in any order without changing anything. So when we flip these, we didn't do anything here. We just put them in a different order. But then making that match in the permutation causes a negation because it's switching two elements in the permutation. And we proved in 3.1 that if you swap two elements in a permutation, you negate the sign. Then it's just moving that sign outside, recognizing this is the definition of the determinant of A. So we get determinant of B is negative determinant of A. Okay, let's go ahead and do a similar proof for part 2. So let's actually, So property 2. So now we'd like to, this was proof of P1. So here's P2. So B is constructed from A by multiplying a row by non-zero scalar k. Again, let's do our sort of same thing. We need to do our need to show. That means that we need to show that the determinant of b is k times the original determinant. Same thing, let's say without loss of generality, assume it is row r that is multiplied by k. So we can then say that the bij elements, well, they're identical, aij, if I is not equal to r, and they are k times aij, I equal to r. So, in other words, all the elements except for the ones in that rth row are equal to aij, and in that rth row, they're just k times aij, or arj, because since we know I equals r. Okay? So now we can take the determinant of b and write out an expression for it. It's the sum over the n factorial different permutations. The sign of each permutation times a1p1 down to anpn. Once again, let's write this out a little bit more thoroughly and highlight when we hit that rth row. So I would say that, oh, and again, I made the same sort of typo. These are b1p1, bnpn. Okay, of course, because it's matrix B that we're working with initially. So now the determinant of B is the sum over the n factorial permutations, the sign of P1 down to PR down to Pn, B1P1 down to BRPR down to BNPN. Okay, now again, let's do our same thing. These ones here, this is where we're not in that rth row, so we can just replace them with those. And this one right here, this is where we're going to be in this position, so we can replace it with the multiplication by k. So we get that the determinant of b here is the sum over those n factorial different permutations, the sign of p1 to pr to pn, a1p1. This is going to become k arpr. And then this down here is just going to be ANPN. Okay. Now, remember, this is a big multiplication of scalars, so you can multiply this however you like. You can put the k out front, but of course you could also just take that k and stick it all the way to the front there. So we're going to now move this k all the way out to the front. So we have the determinant of b is k times the summation n factorial permutations, sine P1 through PR through Pn, A1P1 down to ARPR down to ANPN. You will notice that this is exactly the definition of the determinant of A. We didn't interchange anything this time, so we don't have to negate. This is exactly the determinant of A now. So this whole thing, that's just the determinant of A. So we get determinant of B is K determinant of A. And that's what we wanted to prove, and we're all done there. So proving property 2 much easier than property 1, because this one, we only multiplied one row by a scalar. You just have all the elements multiplied by that scalar. You throw the scalar out front. You're all done there. Okay, so the main idea from this now is if we sort of go back, we now know how each of the 3 elementary row operations, interchanging 2 rows, multiplying a row by a non-zero scalar, and adding a multiple of one row to another row, impacts the determinant. If we link this with what we said here, that the determinant of an upper triangular, lower triangular diagonal matrix is just the product of the diagonal, we get our first major computational technique for calculating determinants. Obviously, you have the definition, but as we saw, 3 by 3, 4 by 4, or beyond, it gets very messy. So now our new computational technique is to say you can use your elementary row operations to put a matrix into upper triangular or lower triangular form, then use this theorem. All you need to do is make sure that you keep track of what elementary row operations you performed and how those impact the determinant, so you can determine the original determinant at the end. So let's go ahead and take a look at how to do that, and also just some nice notation. So here's a 4 by 4 matrix, which would be very messy to try to use the straight definition. So again, you don't need to use the straight definition. What we're going to do is, just as a little bit of review, we're going to calculate the rank and the determinant of this matrix in our new method, which is going to be trying to put it into a sort of upper triangular form We're going to do upper triangular in this case because we also sort of want to get the rank, and we know that if we put it into upper triangular, that's very similar to row echelon form, so we'll be able to figure out the rank, and we'll be able to figure out the determinant. So let's go ahead and start by looking at our original matrix here. So I'm going to write it as sort of 3, 6, 0, 3. Here we go. I'm just going to rewrite it initially, just to also give us some nice notation. 2, 4, 2, 1, 3, 6, 0, 7. And I'm going to just keep track on bottom that currently this guy has its determinant as determinant of A. All right, so let's perform an elementary row operation that'll help us move towards sort of an upper triangular or row echelon form. It might be useful to have this up here so we have a leading one and then we can clear out everything below it. So let's go ahead and perform the row operation R1 interchanged with R2. So in terms of the matrix, we have 1, 5, 0, 3, 3, 6, 0, 3, 2, 4, 2, 1, and 3, 6, 0, 7. Now, this, of course, this is a row equivalent matrix to this. This matrix is not guaranteed to have the same determinant. Interchanging two rows negates the determinant. So this matrix right now currently has negative the determinant of A. So if we, for some reason, magically knew that the determinant of this matrix was negative 5, well, we would know that negative determinant of A equals negative 5, and we could say that the determinant of our matrix was 5. Now, of course, we don't magically know the determinant of this, so this doesn't help us yet, but we got to keep track of how these row operations impact our determinant. Okay, now we can do another sort of operation here. Let's go ahead and do sort of 3 operations. Let's take R2 and replace it with R2 minus 3 row 1. Let's take R3 and replace it with row 3 minus 2 row 1. And let's take R4 and replace it with R4 minus 3 row 1. So in other words, I'm going to use my leading one to clear out everything below it. So if we do that, my first row isn't going to change, 1, 5, 0, 3. Then we're going to get 0, 6 minus 15, so that's minus 9, 0, and then 3 minus 9, that's going to be negative 6. Then we're going to get 0, 4 minus 10, so that's going to be negative 6, a 2, and 1 minus 6, so negative 5. And then down here, we're going to get 0, 6 minus 15, so negative 9, 0, and then 7 minus 9, so negative 2. Okay, now these are all the third type of elementary row operation, which we said does not impact the determinant. So doing 3 of them, not going to impact the determinant. So we still have negative the determinant of A. Okay, now we can continue from here and continue our sort of manipulations. So it might be sort of useful to get this. We don't have to get it to be a leading 1 necessarily. So let's just divide this by, say, negative 3 and make things a little bit easier there. So let's do negative 1/3 times row 2. So if we do that, we get 1, 5, 0, 3. Looks like 0, 3, 0, 2, and then 0, negative 6, 2, negative 5, and 0, negative 9, 0, negative 2. Again, there's going to be lots of different paths you could take, but I'm going to do this one. This is multiplying a row by a non-zero scalar, so it's going to multiply my determinant by the same thing. So now this matrix has 1/3 the determinant of A, because negative 1/3 times the negative determinant A means we now have 1/3 the determinant of A. Okay, we can now use this to clear out the stuff below. So let's go ahead and do R3 and replace it with R3 plus 2 row 2, and R4 with R4 plus 3 row 2. So we have 1, 5, 0, 3, 0, 3, 0, 2, and then we're going to get 0, 0, looks like 2, and then negative 5, what is that, plus 4, so negative 1. And then down here, we're going to get 0, 0, 0, and then that's going to be negative 2 plus 6, so we're going to get 4 there. Yep, okay, there we go. So that doesn't look too bad. And of course, these are the third type of elementary row operation, so they do not impact the determinant. So we have 1/3 the determinant of A still. Now you will notice that this is upper triangular. So this is upper triangular now. So we can go ahead and calculate the determinant of this. So now I'm going to use this notation. Determinant 1, 5, 0, 3, 0, 3, 0, 2, 0, 0, 2 minus 1, 0, 0, 0, 4. Keep in mind when you change to sort of straight lines instead of brackets, this means determinant. This is going to equal 1 times 3 times 2 times 4, which is going to equal 24. Does that mean our determinant is equal to 24? No. That means the determinant of this matrix is 24. And we know this matrix has 1/3 the determinant of ours. So now we can finish up by saying 1/3 the determinant of A is equal to 24. And that means that the determinant of A is actually equal to 72. So there we go. If you wanted to, you could try using the brute force approach and go through all 24 permutations, keep track of everything, sum it all up, and you will get 72. This, of course, is much easier as long as you sort of keep track of your operations and keep track of how they impact the determinant. This is going to be a lot faster here. All right, I'd also like to just briefly talk about the rank. You will notice that this is not in row echelon form, but it would be what I would call quasi-row echelon form. The reason I say that is that the only thing that's not in row echelon form is that these are not leading ones. But of course, I could go through and do 1/3 R2, 1/2 row 3, and 1/4 R4. That, of course, would put all leading ones. The main thing, though, is that since it's got that sort of format where everything below the leading values are 0, you can tell how many non-zero rows there are. So you can also see, just from here, that the rank of A is equal to 4. So this is a square matrix with full rank because we have 4 non-zero rows. Even though we didn't go all the way fully to row echelon form, it shouldn't be hard to see that we are only one scalar multiplication step away. So you can deduce the rank from this sort of quasi-row echelon form. Did we know that the rank was 4 back here, or from the very start? Not at all, because again, it wasn't even close to row echelon form. Once you got it where the only thing off is that they're not necessarily leading ones, they're just leading non-zero values, then you can determine the rank. Okay, so speaking of rank and determinant, now that we've sort of seen an example of how these row operations impact the determinant, we're ready to prove the sort of major theoretical result that does link the determinant, rank, and invertibility. Remember, we came up with this idea of the determinant solely to come up with a sort of numerical property of a matrix that relates to invertibility. And then we're now ready to mention that. So this is a very sort of important theorem. This says if A is a square matrix, then A is invertible if and only if the determinant is non-zero. So this is an if and only if statement, meaning it does read both ways. So you actually get a bunch of information here. You get that if A is invertible, then the determinant of A is non-zero. If the determinant of A is non-zero, then A is invertible. If A is not invertible, then the determinant is 0. And if the determinant is 0, then A is not invertible. So this gives you 4 different pieces of information. Notice that if we applied this theorem back to here, we would be able to tell that since we got the determinant to be 72, which was non-zero, this must be an invertible matrix. Notice that that matches with what we said in the invertible matrix theorem, that a matrix is invertible if and only if its rank is full. And notice that the rank here was full. It was equal to the 4, which was the number of rows and number of columns. So this gives us a sort of another way of diagnosing which matrices are invertible and which are not. So we got to go ahead and prove this. So this is an if and only if, meaning that there are actually 2 proofs in here. So we're going to do, we'll prove this direction first for the forwards direction. So we get to assume A is invertible, and we need to show the determinant of A is not equal to 0. So this proof is going to be basically based on those elementary row operations. So let's recall what it means for A to be invertible. Remember, A being invertible, we know that that means A inverse exists. We know that that means that rank of A is equal to n. And we also know that that means A is row equivalent to the identity matrix. We're going to use that last one. So A invertible implies that A is row equivalent to the identity matrix. Okay, so there's a series of elementary row operations that takes us from matrix A to the identity. Well, that tells us, right, if we go all the way back to sort of what we started with, we gave this corollary here that said if B is row equivalent to A, then there's some non-zero scalar C such that the determinant of B is equal to C times the determinant of A. So what that means for us here is that if A is row equivalent to IN, then there exists some C not equal to 0 such that the determinant of A is equal to C times the determinant of the identity. So in other words, there's some non-zero constant that relates the determinant of A to the determinant of the identity. What is the determinant of the identity? Well, the identity matrix is a bunch of 1s on the diagonal and 0s elsewhere. That means it's a diagonal matrix with all 1s on the diagonal. By our very first theorem, that means that the determinant of the identity matrix is 1 times 1 times 1, all n times, which of course is just 1. So this tells us that the determinant of A is C times 1, which means that the determinant of A is equal to C. And since we know that C is non-zero, we know that the determinant of A is non-zero. So that's what we wanted to prove. So that's our forwards direction. Now let's go ahead and prove the reverse. So now we're going to prove the other direction. So we're going to assume the determinant of A is non-zero, and we need to show A is invertible. Okay? So we get to assume that the determinant of A is non-zero, and we're going to try to show that A is invertible. So let's go ahead and start with, let's let A star be A in reduced row echelon form. So we know that A is equivalent, row equivalent, to A star. So A could be any matrix, but we're going to let A star be A in reduced row echelon form. So since we're trying to show that A is invertible, then if we put A into reduced row echelon form, then trying to show that it's invertible is equivalent to showing that A star is the identity. So we need to show that A star equals the identity. Because, remember, reduced row echelon form is unique. If you're going to be invertible, then your reduced row echelon form can't have any 0 rows, because otherwise you wouldn't have full rank. So you have to have all non-zero rows, which means your reduced row echelon form has to be the identity. So we need to show that A star equals the identity here. Okay, so let's go ahead and take a look at what that's going to sort of look like here. So to do that, what we're going to go ahead and do is we're going to examine sort of what we can say about the determinant here. So we're actually going to do this as a little bit of a proof by contradiction. Okay. So, well, let's see. Do we want to do it as a proof by contradiction? No, I'm sort of wondering if we really need to. Do we want to? Yeah, let's go ahead and do it as a proof by contradiction. Yeah, that'll be sort of fancier than how I would normally do it. Okay, so let's do a proof by contradiction. So let's assume A star is not equal to the identity. Well, the only way that a reduced row echelon form is not going to equal the identity is then A star has a 0 row. Right? So once you put it in reduced row echelon form, A star has to have a 0 row. Well, if A star has a 0 row, well, and it's in reduced row echelon form, then we've got something that, we've got some 1s on the diagonal, and then at some point we run into some 0s. That tells us that the determinant of A star is going to be equal to 0. Okay? So the determinant of A star must be equal to 0. But remember, A star is A in reduced row echelon form. So A is row equivalent to A star. So this would tell us that the determinant of A is some scalar times the determinant of A star. But that would tell us that the determinant of A is C times 0, which would tell us that the determinant of A is 0. But remember, our baseline assumption was that the determinant of A is not 0. So this is a contradiction. So what was the only additional assumption we made is that the A star was not the identity. So A star must equal the identity, which means that A, which is row equivalent to A star, which equals the identity, is invertible. So we've shown that if the determinant is non-zero, then A is automatically invertible. Now, I think in your book they prove this as well, and I don't think they use a proof by contradiction. I think they do it directly, which is how I would normally do it. But since it's been a little while and we haven't really seen a lot of proof by contradictions, I wanted to do one there. I think you could just do it directly by making an argument directly from just saying that since the determinant of A is non-zero, that means that the reduced row echelon form can't have any zero rows, therefore it has to be the identity. But I sort of like this proof by contradiction. Main idea here, of course, is that if it's not equal to the identity, it must have a zero row, which means its determinant must be zero, because there has to be, it's going to be in upper triangular form since it's reduced row echelon, but since it has a zero row, there's a zero on the diagonal, so its determinant is zero. That means the determinant of A is zero, but of course we assumed it wasn't. So there we go. This is a very, very sort of important theorem for us, because this relates invertibility to the determinant. And this, of course, is why we established the determinant. Now we know non-zero determinant is the same as being invertible. Okay, let's wrap this up with just a couple quick examples, sort of using our new approach for calculating determinants and confirming that this theorem really does make sense. So we're just going to do a couple computational examples. We're going to look at a pair of square matrices here in A and then the next one B, where we're going to try to determine the rank, the determinant, and A inverse if it exists. So we'll go through and we'll sort of do all this stuff together. We'll also see that there's sort of a good way of keeping track of everything so that you can sort of do all this simultaneously without having to sort of repeat your work. So let's go ahead and start by rewriting our matrix here. So we have 2, 0, 5, 1 minus 3, 4, 4 minus 6, 13. Let's augment it with the identity matrix. Why am I doing that? Well, because eventually, if A inverse exists, I'd like to find it, and we know that the only way we've talked so far about finding an inverse is to turn this into the identity, and then what happens here is the inverse. But let's also keep track of the determinant. We know that this has determinant A right now. Okay, so let's go ahead and proceed from there. First thing we probably want to do is maybe we want to get this up here so that we have a leading 1, makes things a little bit easier. So let's interchange row 1 and row 2. So we now have 1 minus 3, 4, 2, 0, 5, 4, negative 6, 13, and we have 0, 1, 0, 1, 0, 0, and 0, 0, 1. And of course, this operation here in terms of determining the determinant is negative the determinant of A right now. Okay, so now we can use this to clear out the stuff below. So let's go ahead and do R2 and replace it with R2 minus 2 row 1 and R3, and replace it with R3 minus 4 row 1. So we have 1 minus 3, 4, then we have 0, and then we have 0 plus 6, so 6, and then 5 minus 8, so negative 3. And then down here we have 0, and then negative 6 plus 12, so 6, and 13 minus 16, so negative 3. And then over here we have 0, 1, 0, and then we have 1 minus 2, 0, and then we have 0 minus 4, 1. Okay, and of course these are the third type of elementary row operation. They do not impact the determinant, so this guy still has the negative determinant of A. Now, of course, we could use this to cancel out, actually completely zero out that part. And that probably tells us that this thing's going to be non-invertible because we're going to get a 0 row here. But let's go ahead and see it. So we're going to take R3 and replace R3 with R3 minus row 2. I think we can squeeze that in here. So we get 1 minus 3, 4. And of course, 0, 1, 0, not going to impact there. 0, 6 minus 3, 1 minus 2, 0. And then 0, 0, 0. And then we're subtracting, so it looks like we get minus 1, minus 2, and 1. Okay, so we get pretty much everything we want right here. If we see this, this tells us that it's going to be non-invertible because there's no way to convert this into the identity matrix. We also have this thing in upper triangular form. So if we multiply 1, 6, 0, we're going to get a determinant of 0. So if we sort of look at all that stuff, we can see that negative, the determinant of A, is 1 times 6 times 0, meaning that the negative determinant of A is 0. So the determinant of A is equal to 0. We will also notice that the rank of A, even though I don't have it in row echelon form, if I just divided this row by 6, I would. I'd have 1 and 1 there. The rank of A is 2. And you will see that the determinant is 0, the rank is non-full, and of course both of those things we now know means that A inverse does not exist. So this one has something that has a determinant of 0, which we just proved means that the A inverse doesn't exist. And of course we know the A inverse doesn't exist because we had our old technique, which is that if the rank is not full and you can't put this into the identity matrix form, then you know that it doesn't have an inverse. So there we go. In sort of keeping track of everything, we were able in one sort of line, one set of work, figure out the determinant, the rank, and whether or not the inverse existed. If the inverse had existed, we would have been able to figure that out too, as long as we kept track of what was going on over here. All right, let's try one more example of that. So here we go. We've got matrix B, which is a 4x4 matrix. We're going to try to determine the rank, the determinant, and the inverse if it exists. So same thing, let's go ahead and augment this. So we're not going to change anything yet. 2, 2, 1, 2, 3, 3, 0, 4. We're going to augment with 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. And of course, we're going to say that this guy, since we haven't changed anything, that has the determinant of B. Okay, we've got our lead 1, so let's get rid of those things there. So we'll go ahead and replace row 3 with row 3 minus 2 row 1, and row 4 with row 4 minus 3 row 1. So when we do that, we get 1, 1, 0, 1, and 1, 0, 0, 0. We're not doing anything to this row, so we have 1, 0, 1, 0, 1, and 0, 1, 0, 0. Then we're subtracting here, so it looks like we get 0, 0, 1, 1, and we're subtracting... no, we get a 0 there. 2 minus 2, yep, so we get a 0 there. And then we get minus 2, 0, 1, 0. And down here, we're going to get 0, 0, 0, and then 4 minus 3 are 1, so that's going to be a 1, minus 3, 0, 0, 1. Okay, these are the elementary row operations that are the third type, so they don't impact the determinant. So we have the determinant of B right here. Okay, actually, we're all good. We know a bunch of things right now. This is in upper triangular form, and it's actually in row echelon. So we can immediately deduce, right, a couple things here. We get the determinant of B is 1 times 1 times 1 times 1. So that tells us determinant of B is equal to 1. Notice that this is non-zero, so we know B inverse exists. We also can see that we have a full rank, so we can see that the rank of B is equal to 4. And we know that B inverse exists. Now, do we know what B inverse is? Well, not quite. We need to finish this up by getting this into the identity matrix form. So we need to use this to eliminate these, and then we can use this guy to eliminate that. So we don't need to keep track of determinant anymore, though, since we already know what it is. So let's go ahead and do R2 replaced with R2 minus R4, and R1 replaced with R1 minus R4. So we get 1, 1, 0, 0, and then looks like we get 4, 0, 0, minus 1. And then we also get 0, 1, 0, 0, and we get 3, 1, 0, minus 1, and then 0, 0, 1, 0, minus 2, 0, 1, 0, and 0, 0, 0, 1, minus 3, 0, 0, 1. Okay, and now we're almost there. We just need to use this row to remove that there. So we can go ahead and replace row 1 with row 1 minus row 2. So we get 1, 0, 0, 0, and then we're subtracting row 2, so it looks like we get 1, minus 1, 0, 0, and then 0, 1, 0, 0, 3, 1, 0, minus 1, 0, 0, 1, 0, minus 2, 0, 1, 0, and 0, 0, 0, 1, minus 3, 0, 0, 1. And there we go. So that tells us that this right here, This is our inverse, so we can conclude that B inverse, which we already knew existed, but now we actually have its expression, is 1 minus 1, 0, 0, 3, 1, 0, minus 1, minus 2, 0, 1, 0, and minus 3, 0, 0, 1. And there we go. In our next video, we'll continue on into section 3.2 and continue to learn some properties of the determinant. We've got some properties about the elementary row operations, but we'll also see how the determinant interacts with other things like the transpose and some other pieces. We'll also talk about the determinant of the inverse, so we'll continue investigating properties of the determinant.